Welcome back to Goddard Space Flight Center in Maryland for the second of two briefings on NASA's next Earth science mission, set to launch 1 month from today. That mission is a Global Precipitation Measurement Core Observatory, which is an international mission led by NASA with the Japan Aerospace Exploration Agency, or JAXA. Our panelists for this briefing will talk about the innovative science and societal benefits that the GPM Core Observatory and its associated constellation of satellites will make possible. Let me introduce to you the three panelists. First, Ramesh Kakkar, GPM Program Scientist at NASA Headquarters. Gail Skowronek-Jackson, NASA's GPM Project Scientist at Goddard Space Flight Center. Enrico Oki, JAXA's GPM Dual Frequency Precipitation Radar Program Scientist. After our panelists have given their presentations, we'll take questions from the media on the phone lines, from those in the audience, and from you watching online via social media. If you'd like to ask a question on Twitter, please use the hashtag AskNASA. Okay, we'll begin. Our first panelist, Ramesh.
Thank you, Steve. So water is an integral part of life on this planet, and NASA plays a major role at the forefront of water cycle research. The water cycle is central to creating an understanding of weather, climate, and water resource management for the society. You got to measure precipitation if you want to study the water cycle. Here are some examples of NASA satellite missions involved in water cycle research. The Tropical Rainfall Measuring Mission, or TREM, Aqua, GRACE, and Aquarius are currently flying and making measurements. The GPM Core Observatory is going to be launched next month, and SMAP, Soil Moisture Active Passive, is going to be launched in later this year. TREM is a collaborative effort between NASA and the Japanese space agency JAXA. Launched in 1997 as a 3-year mission, it's still flying and making measurements. TREM precipitation measurements have made and continue to provide critical inputs in many areas, including tropical cyclone forecasting, numerical weather prediction, and precipitation climatology, and societal applications like irrigation for agriculture, providing help in coping with floods and droughts, and administrating freshwater supplies. This data is used by many domestic and international agencies. The enormous success of TREM led NASA and JAXA to collaborate again on GPM. The GPM Core Observatory, as has already been mentioned, will carry 2 instruments, the Dual Frequency Precipitation Radar and the GPM Microwave Imager, the GMI. TREM is focused primarily on heavy to moderate rain over tropical and subtropical oceans. With the GPM Core, the global coverage of precipitation measurement will improve a great deal, from 35 south to 35 north latitude range covered by TREM to 65 south to 65 north latitude range to be covered by the GPM Core. The GPM sensors will extend the measurement range attained by TREM to include light intensity precipitation down to 0.2 millimeter per hour and falling snow, which accounts for a significant fraction of precipitation occurrence in the middle and high latitudes. We will make data available in near real time, that is within about 3 hours of observation, for scientific research and societal applications. As TREM did before it, GPM will do a very good job of measuring precipitation from space. However, the GPM Core satellite cannot be over every place where precipitation is happening at any given time. And that is why we need constellation satellites. These constellation satellites are cross-calibrated or tuned against the GPM Core. And even if the GPM Core is elsewhere, a constellation satellite that is tuned with the GPM Core is likely to be over precipitation to allow us to make the measurement. The Precipitation Processing System, or PPS, located at Goddard Space Flight Center, is a critical component of the GPM project. It ties together the data from the GPM Core Observatory with the data from the constellation satellites. Data from the core and constellation satellites is sent to the PPS. The cross-calibration of constellation data takes place here. The cross-calibrated data is then made available to the user community, including JAXA's Mission Operations System. NASA and JAXA are the primary partners in GPM, but the constellation data are provided by several international and US interagency partners. In addition, we also have commitment from nearly 15 countries to provide ground validation of satellite precipitation measurements. So the GPM mission is truly an international endeavor. And so that is all for me right now, and now over to Gail Jackson, the NASA project scientist for GPM.
Thank you, Ramesh. GPM really is a global mission, and we need that global team to be able to validate precipitation products all over the world. And this is because the rain that falls in my backyard may be very different than the rain that falls in the backyards of families worldwide. We really do need to care because less than 1% of all the water on Earth is easily accessible for us to use as freshwater resources, and water is vital to life on Earth. We need to measure precipitation both frequently and at the local and regional scales so that we can follow fresh water through the water cycle of the Earth. How do we measure global precipitation? We use the GPM Core Observatory as an anchor to hold together all the rest of the constellation members. And this is going to provide us the most accurate and advanced precipitation measurements to date from NASA satellites. The GPM Core Observatory has some special engineering features, and the features on the DPR radar are that we are able to have what we call a CAT scan. It's a three-dimensional view of the precipitation. And it's just like seeing three-dimensional within the cloud. The GMI, on the other hand, I like to describe as an X-ray through the cloud. And it's a projection of the liquid, all the liquid in the cloud and all the ice in the cloud. And just like a doctor uses CAT scans and X-rays to diagnose what's happening in the human body, GPM Core Observatory is going to use its measurements of the radar and the radiometer to diagnose the precipitation structures within the cloud. This is very, very important because we're going to be able to get varied time scales. Every 500 meters, we're going to be able to get the drop size distributions, and then we have about a 5 kilometer footprint on the ground. This is important not only for finding out the rain in your backyard, but also globally. We also use the GPM Core spacecraft as a transfer standard so that we get these next generation uniform precipitation products everywhere in the world, and that is every 3 hours. And as was mentioned earlier, not only do we get the products every 3 hours, but we have near real-time release of the data. This means that every 90 minutes when we collect the data, within 3 hours after collecting that data, the data will be publicly available on the Precipitation Processing Center here at NASA Goddard for anybody to take. We need to share the precipitation data near real time because of societal application users. Can you imagine if flood forecasting and landslide forecasting has estimates within 3 hours after data collection, every 3 hours, all day long. That means that the emergency planners can evacuate if necessary. In order to enhance the societal applications and the scientific research of GPM, we need to measure all the way down to we need to measure rain rates from the lightest rain rate all the way up to the heaviest rain rates. So we are actually going from 0.2 millimeters an hour all the way up to 110 millimeters an hour, and we're able to detect snow. And this is important because there's some areas of the world that get all of their rain in very, very light rainfall events. Other areas of the world may have these periodic monsoon seasons where they're getting very, very heavy rain. And there's other parts of the world that get a majority of their fresh water through frozen precipitation. We need to measure all those phases. On the other hand, for drought and for early famine warning when you think your crops are going to fail, we need to know how little it's going to rain too. And GPM is going to be able to tell us that as well. Because of these additional features on the GPM Core Observatory for measuring snow, we're going to be able to measure those large type of snowfall events and blizzards that have recently been impacting the Northeast U.S. and other places of the world. The Global Precipitation Measurement Mission is a global team to measure global precipitation, and we're really looking forward to its launch in 1 month. Thank you. Rico, okay, please.
Thank you, Gail. The GPM will provide critical new information for a number of weather and natural hazards that are unique to Japan's part of the world. Japan is located in East-North Asia and affected strongly by Asian monsoon climate. We have 4 beautiful distinct seasons. June is a month-length rainy season. Every year in autumn, our life is affected by several typhoons approaching to Japan. In winter, northwest monsoon wind from Eurasia becomes wet, blowing over Japan Sea and bring a lot of snow in Japan's seaside along the central mountains. People in not only Japan but also in Asian countries in Southeast Asia live with the blessings of snow monsoon and its rain. But at the same time, we are exposed to danger by water-related disasters. Actually, the most deaths are because of water-related disasters among natural disasters, not because of earthquakes or others. For example, in the middle of October last year, landslides from Typhoon Wifa killed more than 30 on Japanese island of Oshima, that is 120 kilometers south of Tokyo. Heavy rain, such as more than 100 millimeters per hour, continued several hours, and rain amount exceeding 800 millimeters during 24 hours was recorded. More recent terrible case was maybe the super typhoon named Haiyan, which struck the Philippines and caused destructive damages. In addition to human life, economic damage by water-related disasters has big impact. For example, the big flood in Thailand in 2011 had serious impact with extensive economic damage to many Japanese companies because there are many Japanese industries factories in Thailand. This shows that not only our own country, we need to know weather and environmental information in global scale due to globalization of economic activities. So detailed three-dimensional distribution of rainfall inside typhoons was first observed by the precipitation radar on board the tropical rainfall measuring mission satellite that is going ahead of GPM. That is observation by TRIM. Thanks to TRIM, now we have accumulated a lot of knowledge on tropical rain systems. So if we looked at the annual change of rain and snow area in global scale, we can see the seasonal march of rain systems. Rain bands move between north and south. The major rainy latitude is, of course, in the tropics. But the second major peaks of rainy latitudes are in the mid-latitude caused by extratropical cyclones. We are sure that GPM will bring us detailed information including precipitating particle information with its vertical structure in precipitation systems in mid and high latitudes, as Trim brought us for rain systems in the tropics. The combination of DPR and GMI has capability to observe liquid and solid precipitation particles from the tropics to the mid and high latitude. Dual frequency radar called DPR has a new Ka band channel which can detect snow and weak rain. We are very excited that we will see completely new information of mid and high latitude precipitation systems that has never observed by a satellite precipitation radar. Information on global precipitation, which will be delivered in near real time, will be utilized in various areas such as flood, drought warning, agriculture, weather forecasting, and global warming research. For example, the Meteorological Agency of Japan, JMA, will use GPM data for their numerical weather forecast. They have a plan to use GPM data directly for their data assimilation in their routing system. And indirectly, they will also use GPM data to improve their forecast models in their model validation. The International Center for Water Hazard and Risk Management, ICHAM, under the auspices of UNESCO, will use global rain map data from GPM for their flood forecasting system. ICHAM has developed and distributed a tool called the Integrated Flood Analysis System, IFAS. IFAS uses the satellite-based global rainfall map and ground-based observation data as input to the river runoff model and calculate river discharge. By introducing this system, local agencies can obtain information needed for flood prediction and/or alert, and can disseminate evacuation instructions and information to residents. Precipitation is one of the most basic and important environmental elements relating to our daily life. We believe that rain and snow information observed by GPM will be the benefit of all. Back to you, Steve.
Thank you, and thank you to all our presenters. All right, we'll take questions now from people on the phone line, the media, as well as from social media. If you are watching online right now, you can ask a question with Twitter by using the hashtag AskNASA. We did have some questions from our previous briefing the media had that I wanted to just put back into the mix here. So let's start with one of those. Could you give a specific example of how GPM will support climate science? Gail, could you start with that?
Certainly. So the question has to do with how GPM is going to help with climate science. And as I mentioned during my little time period, we have these measurements layer by layer within the cloud. And what they tell us are the drop size distributions, specifically how many small particles we have, how many large particles we have, and how many particles in between. Climate models have a very simplistic, well, they're evolving over time, but they don't have that level of detail in their climate models. So the information that we're obtaining from the GPM Core Observatory in terms of the overall measurements and their fine scale and accuracy, as well as, and then putting that into the model, that's good. Another aspect is that the global nature. We will have precipitation estimates every 3 hours, everywhere in the world, and with a little bit of post-processing of our data, we can actually bring this down to every 30 minutes at a 10-kilometer resolution. And that kind of knowledge about global precipitation can help to constrain climate models.
Okay, thank you. And we have a question on the phone lines now from Stephanie Ogburn at Climate Wire. Go ahead, Stephanie.
Thanks. You just answered part of my question. That was from the earlier session, but I wanted to follow up. So what you said about more accurately measuring drop size distributions, will that help better parameterize climate models and their understanding of aerosol cloud interactions? And then also I was wondering if you could speak a little bit more about how the constellation of satellites is used along with GPM to get a global picture of precipitation.
Okay, let me perhaps repeat one of those questions. It was a little bit staticky. It had to do with the drop size measurements of the precipitation. How will that aid science in terms of the aerosol cloud interaction and in the climate models?
So I will take a stab at probably both of these questions. So the Global Precipitation Measurement mission is really only looking at particle sizes that are big enough to fall out. NASA has other missions that are looking at the aerosols and at the clouds. And hopefully, over time, we put all the data together from multiple satellites to get the complete picture from aerosols to clouds to precipitation. I think that was the first question, right?
Right.
You want me to answer? Go ahead.
Repeat the second question. As you
The
understand.
second question, as I understood it, was how does the GPM Core Observatory work together with the constellation members to get the global precipitation? Okay, so it's really a two-step process. First of all, on the GPM Core Observatory, we have the GPM microwave imager, which is a radiometer. All the other constellation members have radiometers. They're slightly the same, slightly different. And each constellation member has their own purpose, their own reason for existing, and their agencies use them that way. But they're willing to share their data with us. So the first step in the process is to make sure that those measurements have no bias in them. And that's the first step. The second step is to take the GPM Core Observatory data, both the layer by layer information that we get from the DPR, as well as the microwave imagery that's more like the X-ray. We put those together and we make what we call a database, an a priori database, which just means this is the truth as the GPM Core Observatory sees it. Then we use that database as the core element for retrieving all the other constellation members. So that way we're actually taking the information from the radar, from the Core Observatory, and applying it to all the other constellation members. And that's how we get the uniform next generation precipitation estimates everywhere, every 3 hours.
Okay, let me add something to that. Right now, all these constellation satellites are being cross-calibrated against TRMM. And so hopefully we'll have some overlap between TRMM and GPM, which will allow us to transfer all the cross-calibration that we have developed for TRMM to GPM. And actually this also in a way answers the first question also, which has to do with the climatology. For climatology, you, apart from fixing the models, you also need a very large, long database. So we already have 9 years or 13 years worth of data from TRMM, but by transferring these standards from TRMM to GPM, we will extend this database further. And in fact, it's possible to go back in time. Even when TRMM was not flying, the effort that we have put into this cross-calibration at NASA, with that effort, we can go back in time. We can now find another DoD satellite which was flying when TRMM was not flying, but now it is now cross-calibrated against TRMM. So to answer fully the first question, Gail answered that we will improve the models, but we can also improve upon the length of the database that we have by transferring these standards.
Thank you. I had two other questions that came in earlier on social media. How will this new GPM technology benefit forecasting of major storms like snowstorms or rainstorms? then.
You want me to answer? You want to answer?
I will try and please
Okay.
add. So as Gail already explained, the particle information inside the climate, weather, the precipitation system modeling is very important. So, and the current model is not treating the details of such information. So, and so the GPM information will be utilized in model improvement, my understanding.
I'll just do a follow-on. One of the benefits of measuring precipitation from space is the problem that exists of trying to do ground-based measurements. And many of the cyclones and typhoons and hurricanes, and even some of the snowstorms, is that they're coming to us from over the ocean. And hundreds of years ago, you would have no idea that a hurricane was coming your way. Nowadays, with satellite measurements, we can see that as it marches through. And not only that, we actually have a really strong science team that's been working with the TRMM data, will continue to work with the GPM data. And that team consists of at least, well, there's 56 principal investigators at NASA, about 30 at JAXA, and then we have probably about 25 international collaborators as well. So putting all this data together, we can actually do better predictions of those hurricanes and cyclones as they come across and into impacting land masses.
Now we have a question from social media.
Let me add
Oh, I'm
something
sorry.
to here.
Just a minute,
Let me add
Ramesh.
something.
Sorry to cut you off.
Yeah, see, TRMM and GPM are unique in many ways. You know, these are microwave-based systems. And most of the time when these storms are present, there is a cloud cover. For the first time with TRMM, we were able to see through those clouds, and it was already mentioned in the precipitation and several, we saw several times here that we can see inside the cloud, we can see all those high towers, etc. They can be correlated with how the storm is intensifying. You know, so we can, for the first time, by seeing through the clouds, we can figure out is this storm going to generate into something massive. And also, once it is formed or the genesis takes place, we can also from TRMM and GPM data figure out whether this will intensify or fizzle out. So for the first time, we have this extra information that we are able to see below the cloud deck.
Okay, thank you. And now for a question from social media.
We have a question that came in from Twitter. And it wants to know if the satellite is able to track individual snowflakes as they fall to the ground, and if so, can it help add to the amount of snow that's actually on the ground that's counted?
I have to answer that one. I love snow. No, we cannot look at individual snowflakes. As I said, the vertical structure is about 500 meters, and that's just a bulk representation of the snow within that or the rain within that 500 meters. So we can't see individual ones yet. I mean, remember, we're at 400 kilometers. Our satellite's at 400 kilometers. That's 250 miles from the Earth's surface. So you really cannot see those small particles. But in a bulk sense, we can tell you in general if the particles are all needles, or mostly all needles, or if they're mostly all aggregates. And yes, this information is important for the snowpack because the amount of snow that falls directly impacts the amount of snow that's on the ground. And there are other NASA missions that are looking at snowpack information, like how much water is in that snowpack, how much ground it actually covers, and what's the depth of that snowpack.
Okay, thank you. That's all the questions we have. Thank you for your questions. So this will conclude our briefing for today. For more information on the GPM mission, there's a website that is www.nasa.gov/GPM. We'll be giving you information there all the way up through launch and beyond. GPM is the first of 5 NASA Earth science missions that we're involved with launching in 2014. It's a very busy year for the agency and for NASA Earth science. We have a website to tell you more about that, all the range of missions. That's www.nasa.gov/EarthRightNow. And as always, you can follow along NASA missions through social media, Flickr, Twitter, Google+. There's quite a few there listed. So please do follow us on the social media as well. Thank you all for watching. Have a good day.